Hi, this is Felix Biesmann. I'm with the Einstein Center Berlin with Bord University Berlin and Amazon Research Berlin. And I'll be talking about joint work with Sebastian Schelter. He's professor with the University of Amsterdam and another colleague of ours at Amazon Research, Tamo Rukat. I'll be talking about Jenga. It's a framework we built to study the impact of data errors on the predictions of machine learning models. And here's the link behind which you can find all the code on GitHub. Why are we doing this? As you know, software systems are being tested, and that's important to test them before you go live with them. You write unit tests, you write integration tests, and you perform user tests. Software systems increasingly contain machine learning components, and as soon as a software system becomes a machine learning applications, it becomes more difficult to test because machine learning models depend on data. If you train on different data sets, you will get a different machine learning model. And depending on the data ingested at serving time, machine learning models will make different kinds of errors. Now, the problem is that real test data is limited and models are often heavily over-parameterized. This is widely recognized in the community. And just two examples here: Google's under-specification paper by Damour and colleagues. It has a couple dozen Google researchers as authors on it, and it talks a lot about this case when you have one limited test set and you have a number of different models that perform equally well on that test set, and then you give those models new data. You stress test those models with different data, and then these different models perform differently, even though they have performed exactly the same or comparably on a small limited test set. And this is due to the fact that these models are under-specified or over-parameterized, and we didn't have enough test data for them. A different angle is also presented here in the stochastic parrots paper by Bender and colleagues, where the authors talk about some of the implications of these effects for responsible usage of machine learning systems in our society. Now, it's widely recognized that machine learning testing is important, and just one more piece of evidence is this great review paper by Chang and others, Machine Learning Testing, Survey Landscapes and Horizons. You see that throughout the past decades, the number of papers published on machine learning testing has become, has grown substantially. Now, how do you test machine learning systems? We use two key ingredients. One is we use a lot of data sets with a convenient API. We are huge fans of Joaquin van Schoren's work on OpenML. It's a repository for data sets which you can access through a simple API. And this makes it easy to test your models on a variety of different data sets. Another ingredient is data corruptions. And this is something that we used in our last year's SIGMOD paper. So Jenga leverages both data corruptions and convenient to access data sets for automation and reproducibility of your tests of your machine learning models. How does this work in detail? So we essentially assume that you have some data set, or you use some data set from OpenML, for instance. And then we provide you with a set of error types that you can declaratively specify to apply on your data. For instance, missing values or scaling. Here is an example for a standard data set where the label is whether or not an applicant gets a loan or not, and the input features are age and income. Now we apply some missing value corruptions and scaling, and we instantiate different corrupted data sets with that, where you see each of these versions of the data set has different values missing here in the age column and different numbers scaled here in the income column. And then we evaluate the impact of those corruptions on the performance of your trained machine learning model. Now, applying corruptions to data is nothing new. The machine learning community has been doing that for decades. One of the best examples, I guess, is Chris Bishop's paper in the 90s, where he has shown that injecting Gaussian noise to data before training a deep neural network on that data is equivalent to applying L2 or Tikhonov regularization on the weights of your neural network, which is also known as weight decay. In other application domains, like in computer vision, also there, applying corruptions is a standard procedure to regularize your model to make it invariant with respect to certain errors. For instance, people rotate and crop their images to make their models invariant with respect to those transformations. Those examples, though, are applied at training time or before training time, and they are being used to make your model stronger, to make it more resilient, and to make it invariant with respect to certain types of errors. Here, in contrast, in Jenga, we assume that your model is already trained and we don't have access to the model. It might be hidden behind a cloud API. This is a use case that we addressed in the Signal paper that I mentioned earlier. So we just try to make it as easy as possible for you to apply corruptions to test your pre-trained opaque machine learning model. So we offer 3 core API components to in Jenga, and those would be the tasks. We consider binary, multi-class, classification, and regression. And we offer corruptions for text, images, and tabular data. And we offer some evaluators that apply the corruptions and test your machine learning model on a given task. Now, here's an example of how to use Jenga on an OpenML dataset, binary classification. We first instantiate this task, which is as simple as this. We just give it the OpenML ID for a dataset. And then each task has a baseline model. Here it's just a simple scikit-learn pipeline, but it's easily customizable. And we can fit that baseline model, and then we get the baseline performance, which is around just above 60% ROC score. Now, we can apply one of the predefined corruptions, which would be for text, for instance, lead speak, for images, standard augmentations. For structured data tables, we would have different types of missing data. And here we support different missingness structures, missing completely at random, missing at random, or missing not at random. Here, from missing completely at random, that's the simplest case. We just, throw a coin, flip a coin, and check whether a value should be discarded or not for a given column. Missing at random means that you condition the missingness in a particular column, or you apply the missingness or the error. You condition that on the values in another column, and missing not at random is the most difficult missingness condition. Here, the missingness depends on the values that were missing themselves. And an example is, for instance, rich people usually don't reveal their income, so it's really difficult to estimate or impute those values when they are missing, depending on the values themselves. And those sampling mechanisms are important because they make these corruptions more realistic. So we also provide them for all other tabular corruptions. For instance, swapping columns, or for numerical data, adding Gaussian noise, or scaling the values. It's also easy to roll your own corruptions. And here is an example for missing values. You just specify this class, inherit from tabular corruption. The constructor gets the name of the column, the fraction of values to be affected. And here we are operating on data frames. If you use as a placeholder symbol for missing values nonce, it's easy to use the pandas API to detect those. And then we define the missingness pattern. Those fields are just assigned in the constructor, and then inspired by the scikit-learn API, which has also inspired many other machine learning frameworks. We just have this function called transform, which gets a data frame. and corrupts your data based on what you previously specified. Now, let's look at an example where we apply two types of corruptions, missing values and scaling. First, we replace 40% of all values, missing completely at random, in one column with nonce, and then we scale 30% of the values in another column, not completely at random. So here's how we do this missingness corruption. We just specify the missingness corruption, name of the column, fraction, missingness type, and placeholder symbol. We transform the data. Here we transform the test data of our task. And then we just look at the data, and we see here there are some values missing. Now, as for the scaling, we import that corruption, and then we specify the parameters of that corruption. We transform that corruption. We transform the previously corrupted data frame again with the scaling transformation. And now we see that there are some scaled values here. And now we can, use that to test our machine learning model. We do that for a number of repetitions to get more robust statistics. And then we use this corruption impact evaluator on our task. And well, essentially, we just provide the corruptions as additional arguments to our evaluate function. And then, it runs these evaluations, and then we see, as expected, without corruptions on clean data, we get the same performance as before, an ROC score of above 60%. And on corrupted data, the performance drops by about 6 to 7%. Now, that's how easy it was to evaluate your machine learning model, to test it on corrupted data. It's below 5 lines of Python code, and it's easy to customize by writing your own error functions and evaluators or tasks. To summarize, I hope I could convince you that machine learning model testing is important, and we provided you, I hope you will find Jenga useful because it provides convenient and extensible APIs to test machine learning models with predefined tasks, errors, and evaluators, with declarative error specification and with realistic error sampling. In future work, we want to work on more and more realistic error generators. And if you're interested in how to use Jenga for your research, you can check out our 2020 SIGMOD paper, Shelter-Ruckert and Biesman, learning to validate the predictions of black box classifiers on unseen data. Thanks a lot for watching. Goodbye.